Hi, today we're going to cover strong induction. And previously we have discussed about induction, and I want to review that before discuss this strong induction. Yeah, induction is a method for proving statement about all natural numbers. It is a new logical inference rule, and it only applies over the natural numbers. And the idea is to use special structure of these naturals to prove things more easily. And this is very useful for reasoning about program, a for loop, or uh, some recursion. So we have an example. Uh, there is a number A is odd. If then the A to the n is also odd. So this n is natural number, and we want to prove, and we know about if there is two odd number when we multiply them together, that should be odd again. So we know A is odd. Maybe we can apply the multiplication of these. That would be odd. Yeah, we need to show each pair. Yeah, like this. So A multiply A is odd. Then we know that. And then multiply A, that's odd. And multiply another A, odd. So we need to show this all possible combination. That's really time consuming, and actually we cannot do all of them. So in this case, we need uh, induction. This is the rule of inference. The P of 0 is true. Then for all k, P of k, if P of k true, then P of k plus 1 is true. So then for all natural number n, P of n is true. So yeah, we can show this inference rule for this P of 5. We know about this. P of 0 is true, and we know this connection, this implication. That's why P of 1 is true. Yeah, then P of 2 was true. Next step is true, true, true. Yeah, all these are true. So finally, P of 5 is true. But this is very time consuming like a previous example. So that's why we need this proof method. So first, we have to prove P of 0 first. Second, um, we need to make a connection between P of k and P of k plus 1. If we assume P of k is true, then prove P of k plus 1 is true, that means there is some connection, and uh, we know that this implication here, that's why uh, this is true. Finally, our claim is true. So yeah, we need these things: base case, inductive hypothesis, inductive step, and finally we need now we can get the conclusion. So we can write down this in English. First, define the claim. Second, find the base case and prove it. That if that is true, we need to find inductive hypothesis. Assume P of k is true for some k, then we can do inductive step. In that case, we can we need to prove the P of k plus 1. Then, if the P of k plus 1 is true with the connection of P of k, that means uh, those two has some implication relation. Because of this, automatically P of k is true, and next step P of k plus 2 is true. So we can conclude the claim is true by the induction. This is an example. We have summation of 2 to the nth, and it from 1 to the 2 to the nth. And this can be written in 2 to the n plus 1 minus 1. Yeah, if we write down each step, you can find this pattern. So maybe we can see the pattern, and so we can make this equation, but we want to show that it's true. So this is the claim. They are same. And base case, when n is 0, the left hand side will be 1, right hand side also 1. So let's assume P of k is true. Then we want to show P of k plus 1 also true. So this is the P of k, and this is P of k plus 1. And let's make their relation. If we know that P of k is true, we can find the P of k plus 1 from that. So by the definition, we can add this to P of k, right? So then we get this equation. So we know this is true. Yeah, this is exactly same to the definition, and we need to simplify this part to show this one also same to the original definition. But yeah, they are same. If we simplify this part, this will be 2 to the k plus 2 k plus second. Anyway, this part can be substituted to this way. This will be this, and this one is same to this, the original definition. That's why P of k plus 1 also true. So that means our claim is true. Yeah, this is about the divisor, so and multiplier, multiplication. It depends on the this equation. 3 is a divisor of 2 to the 2n minus 1. So we can write down these to this. 3k is multiplication of 3, and this is same to this. So we don't know about k, but we can prove this using induction. When n is equal to 0, the left hand side will be 0. 3k can be 0 when k is 0. So this is true. Let's suppose P of k is true for some case. So this is P of k plus 1. We want to show this is true. And in that case, we can divide into two parts here, and we can rewrite this like here, and then we can find that is this form. So it is the multiplication of 3. So we don't know about the inside of that, but anyway, we can find uh, 3 in the each factorization. So, so P of k plus 1 is true, and definitely this claim is true. This is about the summation we have discussed in the report as well, and and this is each case we can use a definition of summation. We can use this equation to find their summation simply. First, we apply the base case, and they are same, and find this induction hypothesis. P of k is true, uh, and this is the k, and this is k plus 1. So we know this is summation. When you add k plus 1 into k, the P of k, uh, then it will be same to P of k plus 1. So let's check it out. So this is the one part. Another part is like this. If we simplify these two, then it will be like this one, and this one is same to this. So that means P of k plus 1 is true, then the claim is true. Yeah, actually, I want to discuss this in the uh, lecture. So anyway, and we also practice coding using this question, and we can uh, solve this by the induction, and I'm going to show another solution later. Checkboard is very interesting. So we have 2 to the nth multiplied 2 to the nth checkboard, and with one skill removed. If we see when n is equal to 1, that will be like this inside of that. We can simply cover using this shape of tile over here. That's it. This is base case. We want to show um, next step k. So maybe k will be like this. Mhm. Uh, but anyway, it is based on multiply by 2. So k minus 1 will be this. But let's assume this one is k. So we can put this, we can cover this. This is true. So how to solve k plus 1? Yeah, these are k plus 1. Yeah. Uh, so we have 4 different quadrants. We know this part is covered by the tile, and but if we put a tile at this corner, all the quadrant has one missing. That is same to this one. That means we can cover all the case. Yeah, this is the solution. So we have uh, claim here. We want to prove this. The base case is when n is equal to 1, there is 4 case. They are all true. Hmm? So when you have p of k is true, yep, this is true. We want to prove p of k plus 1, this part, and so we can place a block over here. Want to make all quadrant will be one block missing. That is same to this part. This is true, 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 true. We solved that problem. Okay.